Okay, in this inferential testing video, we're going to be looking at statistics and probability. So to date, we've spent a lot of time looking at how we choose an inferential test. And remember that inferential testing is about determining whether the findings that we've obtained are significant or not. But what does that actually mean? So we've collected our data, we've selected our statistical test. What we'll get then is what we call an observed value, or a calculated value. That means the same thing. The only inferential test you will need to actually calculate by hand is the sign test. To obtain your observed value or your calculated value using any of the other tests, you would do this using software like SPSS at university, the statistical program for the social sciences. You don't need to worry about that. The only one you're calculating by hand is the sign test. For all of the other tests, you will just be given an observed value. They will just tell you the researcher found the observed value to be 0.466, or the calculated value of S was 2. So we'll do a little bit more work on that later on, but that's where we're at. So we've obtained an observed or a calculated value based on the data we collected from our research. So now, how do we know whether that observed value is significant or not? In other words, how do we know whether we found a real difference between our conditions, or if it's an association or relationship, how do we know whether we actually found a true, real association? This is where statistics and probability comes in. So for mathematicians, this is known as hypothesis testing. So all of our inferential tests, all of our stats tests work on the basis of probability rather than certainty. We can never prove a hypothesis to be true, and that's why I get really upset when I see this proves X, because no, in research, we're never able to prove our hypothesis to be true. We're not testing the entire population. There may be quirks in the research design, there may be bias in our sampling procedures. What's true for our sample may not be true for our target population. So we can never say that any finding has been proven. All we can do is work out the probability that this finding would be true of the population. All we can do is work out the probability that the difference we have observed, or the association that we have observed, is true. And therefore, all we can do is work out the probability that the difference or association that we've observed has occurred due to chance. So at what point do we know whether something is statistically significant? I.e., at what point do we know whether our finding is beyond the boundaries of chance? At what point are we confident that our finding is not due to chance and is due to a real difference or a real association between conditions? I.e., are our results actually meaningful? If they are meaningful, and if we're confident that they have occurred due to a real difference or a real association and not due to chance, then we say our finding is statistically significant, beyond the boundaries of chance. And this is where we need to look at p-values. You would have seen p-values from time to time in our notes. If you've read academic articles, you would have come across p-values, and it's something that's kind of taken for granted. And to be honest, a lot of undergraduate psychologists, even some statisticians, might not truly understand what p-values are or their use. And they're kind of contested as well. You know, we take p-values to be the holy grail of statistical testing, but they come with some problems. But what is our p-value? Our p-value is our probability value. Our p-value is our level of significance. You might see it referred to as level of significance or significance level. It's basically the degree of certainty that the difference or the association or relationship is real, and that the difference or association that we're observing is beyond the boundary of chance. If our finding is significant at this p-value, then the researcher is saying that they are observing a large enough difference or a strong enough association to claim that a real effect has been found, i.e., This hasn't occurred due to chance. This is a real difference between conditions. This is a real association between covariables. It is unlikely to be due to chance. In fact, we are confident that this is a real observation, a real difference, a real association. And therefore, because we're confident, we're going to reject our null hypothesis in favour of our research hypothesis. So our p-value is really the point at which our researcher is confident rejecting the null hypothesis. All statistical tests will involve a p-value. They will always set this p-value before the research is conducted. We'll look later at how you determine a level of significance, but that p-value is always set before you even conduct your experiment or gather your data. So in psychology, we typically set the p-value at 0.05. The p-value is the smallest level of significance at which the null hypothesis would be rejected. If we find a result, if we find that our observed value is significant at p equals 0.05 or p is significant at less than or equal to 0.05, this means we're saying there is a 5% likelihood that the difference we're observing or the observed value that we have obtained would have occurred even if there was no real difference between those conditions. There is a 5% likelihood that we would observe that value even if there is no real difference there. Or if it's an association, we're saying there's a 5% likelihood that the association that we have observed or the observed value from that association would occur if there was no real association between those covariables. So p equals 0.05, we're claiming there is a 5% likelihood that that difference or association would occur if there was no real difference or association. So in other words, what we're claiming here is that we are 95% confident that the difference we're observing or the association we're observing is not due to chance. We're saying that there's a 5% likelihood that these differences or associations would occur if no real difference or association existed. Therefore, on the flip side of that, we're 95% confident that the difference or association is real and is not due to chance. So why p equals 0.05? This is our conventional level, our standard level in psychological research. And you can assume that if the p-value isn't given, that the p-value was set at 0.05 before the research. This is deemed to be the acceptable level of error. Remember that we can never be 100% confident that our difference or association is real and not due to chance. But what we're saying is that we're accepting only a 5% likelihood that our results are due to chance. In other words, we're 95% confident that the difference is real or the association is real. So why 0.05? I'll come back to this slide in just a minute, but it strikes a balance between making what's called a type 1 or a type 2 error. So I just want to go through a few analogies with you, and then we will come back to this slide in just a second. Getting a significant result is like hitting the bullseye on a target. if we hit the yellow section, then our finding is significant. We are confident that the difference or the association is a real effect. We are confident that that difference or association has occurred due to our manipulation of the IV or due to a real association between those two covariables, not due to chance. So this is saying that we're accepting a 5% likelihood that the observed value, i.e. the difference or the association, has occurred due to chance. What we're saying is that there's a 5% chance that that observed value would occur even if no true difference or true association actually existed. So if our data is found to be significant at 0.05, if our observed value falls within this yellow range, we can claim that our finding is significant. We're saying there's a 5% likelihood the difference or association we've observed would occur if there was no real difference between conditions, if there was no true association between those two covariables. We're 95% confident that the difference or association is real and not due to chance. When we're 95% confident, if our value is significant at that 95% confidence level, then it means that we can accept our research hypothesis. Remember, our research hypothesis is the one that says that there is a difference or association, and here we're 95% confident that there really is a difference or association, so we accept our research hypothesis. And that means that we reject our null hypothesis. Our null hypothesis is a hypothesis that states that there is no difference or no association. And here, we're 95% confident that there is a real difference or a real association. But one thing to note is because this is all based on probability rather than certainty, when we set P at 0.05, this means that we're also accepting a 5% likelihood that we reject the null hypothesis in error. Because we are deciding to accept our research hypothesis and reject our null when we're 95% confident, it means that there is a risk. It means that there is a 5% likelihood that we're going to make an error in which hypothesis we accept and which hypothesis we reject. In other words, when we set P at 0.05, we're only 95% confident that our results are real and are not due to chance. There still is a 5% likelihood that our results are due to chance, in which case there's a 5% risk that we're going to reject the null hypothesis in error. So P equals 0.05 is our conventional level of significance, but you'll find that sometimes researchers will go stricter or more lenient. So let's have a look at what happens when we set our p-value at other figures. When we set our p-value at 0.0001, this is saying that there is a 0.01% likelihood, or we're willing to accept a 0.01% likelihood that the results have occurred due to chance. Setting the minimum level of significance at p equals 0.0001, it means our null hypothesis would be rejected at 99% confidence. We're saying we need to be 99% confident that the difference between the conditions, or the association between the covariables is not due to chance. We're saying we're accepting a 99% confidence level. This is like making the bullseye tiny, teeny tiny. Rather than before, when we were accepting only a 95% confidence level, now we're being stricter. We're saying we need to be 99% confident that there is a real difference between these conditions or a real association between covariables. We are leaving very, very little up to chance here. This is going to make it extremely difficult to reject the null hypothesis. Remember that our p-value is the minimum level that we're willing to accept in order to reject our null. And here we're being so strict. We need to be 99% confident that the difference or association is real and not due to chance in order to reject our null hypothesis. So we can see how difficult it is now to accept our research hypothesis and reject our null. It's going to be very, very difficult for the researcher to claim a statistically significant results. It's like having a teeny tiny bullseye that's very, very difficult to hit. So why might a researcher choose to have a very, very strict p-value? Well, when the consequences need careful consideration. So for example, if we're looking at side effects of a drug, we don't want to be just 95% confident that that drug isn't going to kill you. We want to be 99% confident. Perhaps even more so. Perhaps we want to be 99.99% confident that that drug isn't going to kill you. So when there are real-world consequences like harmful drugs, like socially sensitive research that might have implications for particular target populations, then we might want to employ a very, very strict p-value. Let's have a look at the alternative. So sometimes actually we go with really, really lenient p-values. So a p-value of 0.1, we're allowing a 10% likelihood that the results have occurred due to chance. In other words, we only now need to be 90% confident that the difference is real or the association is real. We only need to be 90% confident that our results are not due to chance. We're accepting a 10% likelihood that they are due to chance. This is like having a really, really big bullseye on our target. It's going to be much, much easier to hit, i.e. it's going to be very easy to reject the null hypothesis. Because we only need to be 90% confident that the difference between the conditions or the association between covariables is not due to chance, we're accepting a huge 10% likelihood that the difference or association would occur if there was no real difference between the conditions. So it's much easier to hit the target because that bullseye is now much bigger. We're accepting a much higher likelihood that the results have occurred due to chance. So we're much more likely to claim statistical significance with a very lenient p-value than we are with a much stricter p-value. So why 0.05? Well, it strikes a balance between making it too challenging to find a statistically significant result, too challenging to reject the null hypothesis, and too easy to reject the null hypothesis. So if we go back to our previous slide, why 0.05? If we employ too strict a p-value, then we're making it too difficult to reject our null hypothesis. It means that we're potentially discounting real differences or associations. we are much more likely to reject our null in error. Because we've got such a strict p-value, because we've got such a small bullseye on our target, it means that it's going to be very, very difficult to find for our findings to be statistically significant. We're much more likely to reject our null hypothesis, even if that's incorrect. We call this a type 2 error. More on that in just a moment. If our p-value is too lenient, i.e. p equals 0.1, then we may be incorrectly finding differences or associations that aren't really there. In this case, actually, we're much more likely to reject our null hypothesis in error. So that's why we have a 5% level of significance. This is because it strikes a balance between the risk of making a type 1 and a type 2. So let's just take a look at our type 1 and our type 2 errors. So a type 1 error, this occurs when our result is wrongly accepted as significant. In other words, we are rejecting our null hypothesis, we are accepting our alternative, in error. In other words, it's a false positive. The psychologist is falsely claiming that there is a real difference or a real association, when in fact there is no real difference or association. The results have occurred due to chance. And this happens when we employ a really lenient p-value. When p equals 0.1, we only need to be 90% confident that the results haven't occurred due to chance, which is actually allowing a lot of room for error there. A type 2 error, this is a false negative. This is when a real difference does exist, but we're overlooking it. i.e., we're accepting the null hypothesis, we're saying that there is no difference or association here, when there actually is. In this case, we accept our null, and we reject our alternative in error. So it's a false negative. There is a real difference. There is a real association, and we're rejecting that. Instead, we accept our null hypothesis in error. And this is more likely to happen when it's a stricter p-value, because we're making the target so small that it's very, very difficult for us to achieve significance. We're much more likely to instead say that our null hypothesis is true, even when a real difference or association actually exists. So this is why we set the level of significance in psychology typically at 0.05, because it strikes the balance between these two types of errors and the risk of making each one. Too lenient, and we increase the risk of a type 1 error, and too strict, and you increase the risk of a type 2 error. And if you think about this, actually, the chance of committing each of these two types of errors is inversely proportional. So if we decrease the risk of making a type 1 error, then we increase the risk of making a type 2 error, and vice versa. If we want to reduce the risk of making a type 1 error, then we make our p-value stricter. If we want to reduce the risk of making a type 2 error, then we make our p-value more lenient. Just as another note, another way that we can reduce the risk of making each of these types of errors is to increase the sample size. There are easier ways to think about type 1 and type 2 errors. Here is one of them. A type 1 error is telling somebody they're pregnant when they're not. This is the equivalent of accepting our research hypothesis, i.e. saying there is a difference or association exists when it doesn't. And a type 2 error is telling a pregnant woman that she's not pregnant. This is like accepting our null and saying no difference or association exists when there is. She's clearly pregnant and we're saying she's not. That's quite a nice way to think of it, but my favourite is with the story of the boy who cried wolf. I'm sure you know this story. At the beginning of the story, the boy claimed that there was a wolf. That would be like accepting our research hypothesis, when in actual fact, there was no wolf. So that would be the equivalent of accepting the research hypothesis and rejecting the null in error. So the villagers thought there was a wolf when there wasn't. They thought there was a significant result there when in actual fact there wasn't. So that's at the beginning of the story, a type 1 error. At the end of the story, we can think of this as like a type 2 error. Actually, the villagers thought that there was no wolf and they rejected the null. When in actual fact, they rejected the research. Sorry. So they said that there was no wolf. They said that there was nothing interesting here, when actually there was. So at the beginning of the story, there wasn't a wolf, but they said